Hello students, it is a continuation video of Unit 3 Magnetism and Magnetic Effect of Electric Current. Here we will see a new topic, Basic Properties of Magnets. Using these properties we can describe a bar magnet. Okay. Here the first property is magnetic dipole moment. Let me see what is magnetic dipole moment. You know very well, in your first lesson electrostatics you already seen about electric dipole moment. Okay, we know very well electric dipole consisting of two equal and opposite charges get separated by a small distance constitute electric dipole. The dipole moment P is equal to Q into 2D. You already know. Okay, here we see the magnetic dipole moment. So I consider a magnetic dipole. Okay, here the bar magnet is nothing but a magnetic dipole. Here the south pole and north pole are separated by a distance 2L. Okay, then this is known as magnetic dipole. Here the poles south and north having the same pole strength, that is QM. Then the magnetic dipole moment is defined as a product of pole strength and magnetic length. Okay, here this 2L is a magnetic length. Okay, listen, it is easily defined as the magnetic dipole moment is a product, that means multiplication, product of pole strength and magnetic length. Okay, here the dipole moment is a vector quantity. It is represented by the symbol PM vector. Okay, then we can write PM vector as, listen, that is equal to product of pole strength and magnetic length. This length can be write in the form of vector, then D vector. Okay, D vector is a vector drawn from south pole to north pole. Okay, listen, if we write in a magnitude form, then PM vector modulus is equal to QM D vector modulus. We know very well D vector modulus is equal to, that is 2L. Okay, then we can write PM is equal to QM 2L. Okay, here the magnetic dipole moment having the unit, the SI unit of magnetic dipole moment is ampere meter square. Okay, then the direction of the dipole moment direction is from south pole to north pole, south to north. Okay, here we will see what is magnetic field. In your electrostatics you know about electric field. Electric field is a space around the charge in which a test charge experiences a force. Like that, here magnetic field is a, listen, magnetic field is a region around a magnet where a bar magnet experiences a force. Okay, if suppose it is a bar magnet, I consider this as a region. In this region, if suppose you place one more bar magnet, okay, then this bar magnet experiences a force, that is known as magnetic field. I will say the definition. Magnetic field is a region or space around the magnet within which a bar magnet experiences a force. Okay, this can be written in a equation form. Then magnetic field vector is equal to, it is a force experienced by a unit pole strength of a bar magnet. Okay, then the unit of magnetic field is, we can write Newton ampere power minus 1 m power minus 1, because it is a force experienced by the test charge. Okay, listen, force, the unit of force is Newton, then the unit of pole strength is ampere meter, then this ampere meter became ampere inverse meter inverse. Okay, then we see what are the types of magnet. Okay, types of magnet. Listen, there are two types of magnet. One is natural magnet, and other one is artificial magnet. Example for natural magnets are cobalt, iron, nickel. These are the example for natural magnet. Okay, here this natural magnet having a very weak strength, and the shape of this magnet is irregular. Okay, here artificial magnet, for example electromagnet. Here having our desired strength, whatever you want, because these magnets are only made by humans, so our based on our convenient we can make this magnet. Okay, so it attain desired strength and desired shape. Okay, if suppose you need a bar magnet, or if you need a bar magnet in the shape of cylindrical also. Okay, it is based on your convenience. Here we see the properties of a bar magnet. Okay, here the first property, if suppose a bar magnet is suspended at a point. Okay, if a bar magnet is suspended at a point, it come to rest in the it come to rest and point along the north-south direction. Okay, listen, suppose if we suspend a bar magnet, it come to rest and point along the north-south direction. Okay, magnet have the property to attract the other magnet and magnetic substance. It attract other magnet. Okay, it will attract another magnet or some other magnetic substance. You know very well, iron is a magnetic substance, it will attract. Then aluminum also a magnetic substance, it also attracted by the magnet. Okay, listen, magnet attract another magnet or magnetic substance. Okay, then this attractive force is always greater only at the end of the magnet. Okay, this is because here the magnetic field lines densities are more only at the end of the magnet. So the magnetic so the attractive force is greater at the end of the magnet. Okay, then the fourth point, if suppose a bar magnet of pole strength Qm is break, then we get small pieces of magnet. Okay, if suppose a bar magnet is break, then it will give another magnets. Okay, having the poles at the ends. Okay, if it is a bar magnet, this is a south pole, it is a north pole. These poles having a strength that is known as pole strength. Okay, here this point represent for a bar magnet the south and north pole having same pole strength. Okay, then last point, if suppose it is a bar magnet, this point is known as geometrical center, represented as O. It is the south pole, it is the north pole. Okay, the distance between the two poles is represented as 2L, that is known as magnetic length. Okay, then the distance between the end of the magnet is represented as L, that is geometrical length. Okay, then the ratio of magnetic length to the geometrical length is 5/6, that is equal to 0.833. Okay, always the magnetic length is less than geometrical length. Okay, here we will see the characteristics of magnetic field lines. Okay, we know very well around the bar magnet some field lines are there. That field lines start from north pole and end with the south pole. It is a direction to indicate the magnetic field lines. Okay, you know very well. These magnetic field lines are always continuous and closed curves. Okay, the direction of the magnetic field is from north to south outside the magnet. Okay, always the direction of the magnetic field line is start from north and end with the south pole, and inside the magnetic field lines start from south and end with the north inside the magnet. Okay, then our next characteristics, if you need the direction of the magnetic field line, so we can draw a tangent on magnetic field line. This tangent represents the direction of the magnetic field. Okay, suppose I need at this point I need the direction of the magnetic field, so I draw a tangent on that field line. It gives the direction of the magnetic field. Okay, listen, the tangent drawn on magnetic field line gives the direction of magnetic field. Okay, listen, the magnetic field lines never intersect each other. Okay, listen, magnetic field lines never intersect. If suppose they intersect, at that intersection point if I place a magnetic needle, then at a single moment it can point the two different directions. It is not possible, so magnetic field lines never intersect. Okay, then the last point, see, if suppose I consider this one as a bar magnet, then around it some magnetic field lines are there. Here the magnetic field is strong where the magnetic field lines are closer. Okay, listen, here the magnetic field lines are closer, so at this point the magnetic field is strong. Okay, if suppose here they are not closer, okay, then here the magnetic field is not so strong. Okay, Here our next property, magnetic flux. In electrostatics we already learned about electric flux. Electric flux is represented as phi E. Here magnetic flux is represented as phi B. The electric flux is defined as a number of electric field line crossing through a given area. Here it is a magnetic flux, so it can be easily defined as the number of magnetic field lines. Field lines crossing through a given area. Okay. It is represented as phi B. Then mathematically it can be written as phi B is equal to B vector dot A vector. Here it is a product of two vector, so it is a scalar one. Okay, it is a dot product of two vectors, then it is a scalar one. So we can call flux is a scalar quantity. Because it is a scalar product of two vector. Okay, can be also write in the form of magnitude, that B A cos theta. Here this theta is an angle between B vector and A vector. B vector is a magnetic field vector and A vector is a area vector. Okay, area vector. A vector is a area vector. We know very well. Suppose for this paper, if we draw an area vector, then the area vector must be perpendicular to this plane. Okay, it is a area vector. Okay, you get it? It is a area vector for this plane. Okay, then if suppose here I consider a uniform magnetic field like this, the direction is from left to right. In that place I placed a plane. Okay, then it is a area vector for this plane, then it is a magnetic field vector, it is a area vector. Here the plane is placed perpendicular to the magnetic field. Okay, here the plane is placed perpendicular to the magnetic field, so the angle between the B vector and A vector is 0 degree. Okay, notice here the magnetic field is perpendicular to this plane. Okay, then the angle between B vector and A vector is 0 degree. Okay, if suppose I consider magnetic field, if I place like this, okay, then it is a area vector. It is a magnetic field vector. It is a area vector. Then the angle between the area vector and magnetic field is theta. Okay. Then we can write flux as phi B is equal to B A cos theta. Okay. Here in this case we can write flux phi B is equal to B A cos theta. Theta is 0 degree. Cos 0 became 1. Flux phi B is equal to B A. When a area or the plane placed perpendicular to the magnetic field, then the flux will be maximum. If suppose here it is a magnetic field, I place the that plane parallel to the magnetic field. Okay, then the area vector is perpendicular to the magnetic field. You got it? Okay, then for this case the angle between B vector and A vector is 90 degree. Then the flux phi B is equal to B A cos 90 degree. Cos 90 0, then flux phi B became 0. There is no flux when the plane is placed parallel to the magnetic field. Okay. If suppose the magnetic field is not uniform over the surface, for that case, listen, magnetic field is not uniform over the surface. For this case we consider flux phi B as integral B vector dot dA vector. Okay, we know very well the unit of flux is a scalar quantity. Then it having the SI unit or SI unit of flux is Weber. Okay, it is represented by the symbol WB. We can also find the dimensional formula for magnetic flux. We will find dimensional formula of flux, that is magnetic flux. Okay, phi b. We know the formula, flux phi b is equal to BA. Okay, then how to write magnetic field? Magnetic field is a force experienced by the unit pole. Then it is a area. Then the unit of force is Newton. The unit of area is meter square. Then the unit of pole strength is ampere meter. Okay, if suppose I cancel this, we get an expression Newton meter ampere inverse. The dimensional formula for Newton is a unit of force. Then F is equal to MA. We can write the dimensional formula for force is M L T power minus 2. Okay, then here it is meter, then L, it is ampere inverse. Then solve it, M L square T power minus 2 A power minus 1. It is a dimensional formula for magnetic flux. Then the CGS unit of flux is CGS unit. We can write it in Maxwell. Then 1 Weber can be represented as 10 power 8 Maxwell. Okay, then our next topic is magnetic flux density. That is easy one. Magnetic flux density, it is nothing but the number of magnetic field lines per unit area. Okay, here that area is kept normal to the direction of field lines. Okay, magnetic flux density is a flux per unit area, that's all. Okay, flux per unit area. Here we place this plane perpendicular to the magnetic field line. Okay, the unit of magnetic flux density is, that is Weber meter power minus 2. Okay, then it is also represented in one more unit called Tesla. Then uniform and non-uniform magnetic field. Here first we see the uniform magnetic field. In uniform magnetic field, all the field lines are in a same direction with the same magnitude. Okay, here in uniform magnetic field, the magnitude and direction is same at all the points in the regions. Okay, here for example our local space. Okay, in our present area the magnetic field is uniform. Okay, then non-uniform magnetic field, here the magnitude and the direction different, are both varies. Okay, for example bar magnet. Okay,